the information there, you can go down here and you can see the answers. So I'm just going to go over these 5 problems today. This is not for this Sunday, it's for next Sunday. For example, if you look at the course calendar, you'll see that we might be the lower one. Okay, there we are in statics. That's homework 1. That's on units. Homework 2, which is the one I'm talking about here, is due next, not this coming Sunday, but the next Sunday. So the unit lecture should be pretty much self-contained. So I'm going to go ahead and take this, and I'm going to write on it inside of, now I might be able to open this. Let's see, show all. Okay, open in a folder. And I'll go ahead and open it. Should open it right there. So the nice feature here is I can write directly on this. Excuse me. Let me double check, make sure my audio is still working. Okay, yeah, it's still working. So it says determine the magnitude of the resultant force and its direction measured counterclockwise from the positive axis. So, you know, if I were to say try to make it reasonably accurate, I would take that vector, move it over here, and then, okay, so if this is 800, the length of this one should be shorter. So I'm going to say it's like not that long, but that long. And what I'm going to do, I'm going to grab it, try to do the best I can about sticking it on the end of there. So this one's 800. This one's 500. This one is kicked down 40 degrees. So this is 40 degrees. This one is kicked down 35. Okay, so now if I zoom in, and let it kind of, now I don't have a ruler in here. If I maybe I should have done it in the other thing, but I didn't. So here's my resultant. I'm trying to do reasonable. This is my resultant. Okay, so on this in this section, they're kind of wanting you to do. I mean, you can do it any way you want, but they kind of want you to use these cosine sine things. Law of cosines, law of sines. So here I'm going to I switched color to blue because I'm going to do things like this. This line being parallel to that line. Okay, hang on. Let me get my means that that's 40 degrees. Let's see. So you can work. Well, I don't know why I just did that. You can work this out, and let's see. This part I don't know. What else do I not know? Okay, so I can draw a line back here. If that line is perfectly back to the left, then this blue line right here and this blue line right here are 90 degrees apart. So let's see. 90 minus 40. My brain is not working very well today, so it's not. So don't be surprised if things come up a little off. Okay, so I got 50, 40. I'm sorry. Yes, 50, 40, 35. This red line that heads off over here is approximately, or I'm sorry, not approximately, but it is the same line that's over here. So that, even though I wrote it up there, is 35 down here. So now I've got what's left here to determine, and that would be 180 minus, okay, go ahead and take the 90, because that's the 40 and 50 is 90 minus 35. Well, that pulls me down to, I could have just worked off of this line and that, but I don't know why I didn't. But this is part of the fun of these. Well, if I take that and get 50, then this one should be, it erases a little differently here. Or it doesn't erase at all. Okay. Should be 55. So it gives me 40 and 55, gives me back not 90, but 95. So I got this thing here. This is kind of strange looking, 95. So now, what do you have? You've got the length of one side, the length of the other side, and the angle between them. So just like that, you can use the law of cosines. And that law of cosine will give you this resultant here. So the way that kind of works is the resultant being the length of that vector would just be 800 squared plus 500 squared minus 2 times 500 times another 800, times the cosine of the angle between those two, which this time it turns out to be 95. And so you can calculate that, and once you get that, that's part of your answer. Okay, that's the magnitude. The next part of your answer would be, how far is it kicked up from here? And that's what he wanted to know there. He wanted to know how far is it going to be kicked up from here. Well, here's the deal too. This line is perpendicular to that line, and you know that's 40. You know this is whatever, but whatever can be determined by the law of sines now. And so that would just be basically, I don't know, let's see, sine of the question mark, which is this, look directly opposed to it, that, over 500 equals to, pick your, the one you want. Let's see, the sine of 95, that's this one. Directly opposing that angle is that, the new resultant. Now, the resultant, you would get a number, and you could just put it in here. Then, what you're going to do is take the inverse sine, or arc sine, or whatever you want to call it. Move the 500 over, multiply it times the sine of 95, and then the resultant that you had under there, that is going to give you your question mark, your number of degrees. Once you have that, you know that this angle, and that angle have to all add up to 90 degrees. And so that's what you do. You just basically knock that out that way. That gives you the angle there. Here, vertical force pulling down on this point A right there. Two-member determine the magnitudes of the two components of F acting along this AB, which is this AB is the upper link, AC is the lower link. Set F, set F is equal to 500. So, let's see if we can do a reasonable job. We'll start with the red color. I should put another pen up here, but okay. Okay. I honestly don't know the actual values of them, so I guess I'm going to call this A, and call this one B. Now, these are the forces in the member, and so he wants to know, did he want to know anything besides that? Just determine the magnitudes of the two components along. See, now, technically, this problem should be kind of delayed a little bit, but that's okay. So, you know what I'm going to try to do is I'm going to try to redraw this B. This is going to be an interesting approach here. Here, I'll draw a straight line so I can erase it, but I'm going to just drop a vertical line, and I'm going to start. This is the responses that occur in these two vectors. So now if I add vector B to vector A, I'm going to get a vector that goes up, and that's going to be the same length as that vector, although physically on the drawing it doesn't appear to be. And then I'm going to use the magic of the pen to just sort of drag this over. Now, I got a couple things. I guess I should have left it there just long enough to maybe put my angles in there, and then I'll drag them with the angles. Okay, so let's take a real close look. I can't reduce this any more than 1 point, but here's what I'm going to do. I'm going to go ahead and erase, I'm going to go ahead and erase this so that I can put my angles in here. So this, I'm just copying here, it's 30 degrees. Now, 45 is a lovely angle because 45 and 45 gets me 90. So I can just slap 45s everywhere. So one of the things, I can take this line and realize it's that one. And I can take this vertical line and realize, hey, that one. So I can just go directly in here and put 45 degrees. That's enough information. Now I'm going to copy this, move it over to the side, kind of zoom in on it. Now I do know he told me that this is 500. So I've got this being 500. Hit the escape key. So I got that being 500. Okay, now I know this angle is 90. I know this angle is 30. So I got a 60 there. So suddenly I've got most everything I need. Now what is interesting here is you have law of sines, you have law of cosines, but you also have another fact, and that is that 180 minus the 45 minus the 60, that's going to be your angle that's going to be sitting right there on that other end. And so it's not 90. Okay, so now you've got a situation where, okay, remember, law of cosines, you have to know at least two links somewhere. You don't have that. But you do have law of sines that can help you here. You know every angle, and you know one side. Okay, so I don't know what I called this one before, but I'll make a new symbol here. This will be A, and this will be B. So now you're just looking at sine of 45 over A is equal to sine of, and what it is the opposing, the angle opposing the length. Okay, so pick a length, 60 over B, they're opposing. And then you got the one you do know, 75 over 500. 75 over 500 there. So that's all you need. This will give you a ratio, a number, and then you can do these two, you'll get B, and you do these two together, and you get A, and boom, you're done. There's nothing more he's asking there. So it's pretty much the same thing. I don't know. Okay, he hits 448 and 366. Okay, so here determine the magnitude of the resulting force and its direction measured counterclockwise from the x-axis. So here we go. 26 and 30. Again, looks to me like he has not done a reasonable job as far as his lengths here. So I'm going to take that one, attach it to the tail end of that one. For that matter, just to be complete, I really shouldn't even draw the arrowhead here. Am I getting all of them? Shoot. This is one of those things where you got to select with this. Okay. Okay, you remember I made this thing longer. So now this is kind of disruptive in a way because it gives you the false impression that it's directly down the x-axis, but that's not always the case. But you have to pick one of these to do. You got to pick either this triangle or this one. I don't know. I did a better job on that first one, so I think I'm just going to eliminate this and pick the upper triangle just to kind of keep my focus about me. And I'm going to basically try to do the best I can about drawing this. Now, one of the things I know, and I'm going to draw a few things and then remove them. I got this. I've got, now, maybe I should think about this for a second because he has given me this. That sort of makes me believe that he is more interested in a breakdown as far as a X and Y location. So with this, I'm going to take this and say 30 sine of 30, which is very bizarre. Moving back to the left, so it's minus I plus 30, minus 30 cosine of 30, J, I can put F2 directly under it. This time, I'm going to use the ratios. This is why I think when you see this, it's more often convenient to work yourself in the I and J or the Cartesian coordinates. So now I've got 26, and if I look the ratio for the X, it's 5/13 I. It is going back to the left, is going up 26 times 12/13 J. And all you do is just simply add these together. And then once you add them together, if you want to, well, he says you want to because he wants you to find the magnitude of the resultant. Then you're going to have a vector that's kicking like this, where you're going to have this being F. Okay, so F resultant is equal to, you just add this number, add this one, and put it here. So I'll say F resultant X, I, plus, and add this one, or maybe I'm wrong because it's subtracting, and then F resultant Y times J. Now, he wants to know that angle. So you could use the inverse tangent, but you could also find this resultant and use a cosine or use the sine. With this one over this one, it's kind of up to you. You don't always have to just use the tangent. In other words, tangent inverse. You don't have to use those. You can use the inverse cosine, inverse sine. That's your choice. So let me pick up something on the other side of the room real quick. Okay, sorry for the delay there. Let's get back to it. Oh, wait a minute. Okay, you got that one. And you got that one. Okay, this one should be, in other words, I put these two together, asked two different questions about the same thing. Okay, so here you go. Let's see, is there another one after that? Oh, I did the same thing again. Okay, so here you go. I put these together a year ago, so I have very little memory of them. 750, 625, 850. Okay, so the same thing. I mean, what I would do, got F1 and 2 and 3. F1, what I would do is I would basically go in and break this one down into the X and Y coordinates. This one has a component heading that direction and a component heading down. So that'd be the 850. Heading to the right, the ratio would be 4/5. That's times 4/5. I is heading down 850. And looks like 3/5. So there's your 3/5. And the reason I line them up under each other is because I can add them vertically. In other words, lining them up here, and then when I add them numerically, I can put the IJ at the bottom and just add down. That's the reason I line them up this way. So F2, 625, looks like he's wanting to use 30 degrees, so you're going backwards, and you're doing a sine of 30. You're going down 625 cosine 30. Now up here you got 45. So here's the thing about 45. We love 45 because the sine and the cosine are the same thing, and they're 1 over square root of 2. So we love that because makes things easy for us. We've got a component going to the left. That's 750 over square root of 2. We got a component going up. 750 over square root of 2. And you just add them. And once you add them, you get a number here and a number here. F resultant. Okay, my bet, I don't know this, but there was something I left on the page there. So my bet, since they're both going, there's heavier amount going down than up, that you're going to have a lower component. And as far as the X versus Y, I think there are 2 going to the left and 1 going to the right. So I think that you're going to end up with a point going to the left and a point going down. So that means you're going to have a negative number here and a negative number here. So then, if you want to know your angle, you're basically going to do the tangent of these ratios, but you'll have to also be very careful about this because he wants the direction from the positive x-axis, and maybe that's why I left it there, because when you do the arctangent, you're going to be finding this angle, and there's 180 degrees added to that because he wants it from here. So you're basically going to say, and you don't have to use tangent here, but you could do the f or y over f or x here to get that angle, or you could do a cosine. It really doesn't matter. What you see here is you see 162, and I'm guessing that's Newton, and 520. So it looks like that angle is going to be fairly large, probably 70 or so. And 253, that'd be 180 minus, so that's about right. 180 minus, so add 20, that's 73. So that angle ends up being 73 here. And then you got to add 180 to it. Now, what he does in the next one, he wants them expressed in Cartesian. So that's what he wants. These are what I listed up here. Without doing the math, I just listed them with that. So let's see. 450 times 4/5 hopefully ends up being 680. I don't know what happened here. Okay. So that's pretty much it. So that's the set of problems there. We'll go back into the book, which is, okay, I'll have to do the drop down. Here it is. And what we'll see is all of these problems look the same. Okay, so if you look at them, they all essentially, here he has a situation where he breaks them down into the x and y. So that's essentially all you're doing, finding the result of 3 vectors here, 3 vectors here, 3 vectors here. All you're doing is breaking these. He gives you the x and y coordinates. You can basically break all these vectors down to, like, for example, this looks like the one that we did a minute ago. And so, yeah, okay, so it looks like this is the one I copied. So it's just F1 listed that I plus j. The same thing, you could say it on this one or this one. So any one of these, the equations look the same. You got 3 vectors here. This one, it doesn't designate that this is F1 and this is F2 and this is F3, but you could. And you do exactly the same on all 3 of these because they all have 3 vectors. This one has 2, so you just have 2 vectors. So they all are the same. It's just different pictures. Here's a nice gusset, some nice artist work there, nice artist work there, like a little bolt down thing. So it makes you feel like that somebody spent a little effort here. Here's a funny eye bolt. But the same thing occurs on all of these. Okay, so I'm going to use the last. I'm trying to do as efficient as I can. So this is 1137 up here. What I'm going to do now is go into the last part. Okay. A right-handed coordinate system is an interesting coordinate system, and all of physics and everything is based upon it. If you take your fingers like he has here, you curl them, and as you curl them, now his fingers were straight out, and then he curled them. So he curled them back from the x towards the y, and his thumb points in the positive z action. That is what's called a right-handed coordinate system. A left-handed coordinate system, which is very rarely, if ever, used, would be, instead of using your right hand here, you use your left hand. And what you find out is the positive for left-handed, this would be the Z. This is almost never used. I've only ever seen it used once in anything engineering, and it was used in a very odd way. So, rectangular coordinates. You can break them into components. So you have the main vector A, which is essentially, okay, he probably writes this down here. So he says, okay, we have base vectors pointing in each direction. Therefore, I can write these in this way, where I find out a scalar length that I transverse out the x. That's the length here. This gives you the direction you're going. That is the length, so many feet. Somebody put a ruler down and measured that and say it was 2 feet. So this would be 2 feet, but in what direction? Out the j direction. That's what the base vectors do. They point to tell you which direction you go out there. Nothing new. You've seen it before. Not a big deal. Magnitude. You've seen this before. You want to know the magnitude of the main vector? Take the square root of the square of the sum of the square of the components. Coordinate direction. Here's something new. This is a little bit bizarre, a little bit weird, but what it is kind of this. Excuse me. If, and it's hard to describe this, think of it like this. This is a triangle. Ignore all the rest, and let's just focus on this. This is a triangle in which, if there was some guy standing over here, he would see that. Okay, now, you have to think about this real close, but what he's seeing is this. Okay, so what you have here is a 90-degree, and you have this distance out here. So he has this thing called a gamma. Okay, it turns out that this is the Z, and this is the, I'm trying my best to do this. This is the A component. So now the question is, and so we're just dealing with the Z right here. So if you have this, and I'm just going to make up some numbers so it makes sense. Let's say that this is 10. And then let's say this distance, so I put a ruler down here. So they measured from right here to right here with a ruler, and they found that to be like 9. But they measured from here to here, and it was 10. So then what's the angle between these two? Okay, now look at this. This is a triangle. This is that dreaded hypotenuse, and this is the 90-degree. So if you look at the cosine, and we'll go with him and call this gamma, that's just 9/10. I don't know what that number is. It doesn't really matter what the number is. It turns out that if you look at this, each of these are embedded triangle, just depending on the way you look at it. So that's where these came from. Now, these angles are out in open space, meaning they're kind of three-dimensional. Here's what I mean. He did a good job in describing this top triangle, but let's look at the triangle that exists here. Now, let's see. Hang on. Let me get some of this off the page so I can do a reasonable job. Okay. Okay. So let's look at the 3 triangles here. And these are planes. So if I draw, okay, so he connected the top here to the top here, right? And that defined a triangle in which this was 90 degrees. Guess what? I'm not a great artist, but here is a kind of a strange triangle that's tilted over. It's tilted over, and it's kind of towards you a little bit. Now, guess what? Here's another one. So you could do this and say color this whole thing like red and say that's one triangle. You could also, oh boy, I think I messed that up already. This one's a triangle that is kind of leaning in away from this XZ plane. And so that's a different triangle. So you got three triangles leaning you towards that main vector. So it turns out that, and we'll find this out later, actually this would be a good time to introduce dot products, but he doesn't right now. Which in fact, that's what this is. You know, if you think about what a dot product is, and I think you've had this before, two vectors, okay, A dotted with B is equal to the magnitude of the two vectors times the cosine of the angle. Usually they may list it the angle between A and B. Now, that's exactly what this is, okay? Let's think about this for a minute. Okay, you got two vectors that instead of being A and B, they're not A and B, they're the components of them. And so this cosine actually ends up, you can move these over. This cosine becomes the angle between these two. Think about this, okay? What is between A and B? Well, here's one between here and between this line is that. Okay? Between this line and between that one, what's between those two? This. Just so happens this is in 3 dimensions. What's the cosine, or what's the angle between this line and that one? Well, it's this beta. So in fact, this is directly related to a dot product, which he introduces later, so I think I'll just tell you that it's related to it and say, hey, we'll pick that up later. So with that, what can you do? Well, interestingly enough, and obviously I've been hacking around on this page from last semester. Let's think about this. If, say, I wanted to, and somehow I got smaller print to come out last semester, because my print, anyway, I don't know what I did. So let's think about this. I want to find, so here he does a pretty good job. You've got your 3 triangles, kind of a bluish one, light green, and kind of a very light tan one. There's your 3 triangles. Now your goal is, I may have this vector. I want to find its direction only. What did a base vector do? A base vector gave you the direction. If you were to go this direction, so many feet, you would end up right here. If you were to go this direction, in so many feet, you would end up right here. And then if you were to go in the k direction, end up right here, and you add them all together, that's your vector. But now I want to know, if I just wanted to know the direction, I need to go, that's it, and then how many feet I need to go. I could go from here so many feet, and I'd end up at the same spot. Okay, so again, think about it like this. You're traveling to this point. You go down I a certain distance, then you go down J a certain distance, and then you go up K a certain distance, and you got there. Now, somebody else says, I want to walk less. I want to walk directly from this point to that point. What direction do you go? This direction. How do you find that? Actually, it's quite interesting. It's the ratios, okay? So if you think about it, the base vector is the ratio of, say, for the x, it's the ratio of this length to the overall length. And so forth also for j and also for k. Guess what? From the last page you realize, oh, that's just nothing more than that. Well, guess what? Take a square. Okay, so these are the base vector. This is a base vector, so to speak, a direction vector, a unit vector. He will call it a unit vector. I keep calling it a base vector But actually, he's right. I'm not necessarily, I guess I'm wrong in that. This is what's called the unit vector directing you directly to the point A. And it turns out from the relationship we had before, the cosines help us. Now, if you look at the length of the base vector, it was set to be 1. And it turns out, if you look at it, take the square root of those, what do? You take the square root of the sum of the squares of the lengths, and that should give you the length. It's a unit vector. These are the components. So there is a situation that forces you to have a relationship between alpha, beta, and gamma. So the key is this unit vector, we'll use it a lot. Okay, and so here he basically says, okay, and there's me hacking stuff up. He's basically saying, okay, I can go in and write this 3 different ways. One, a base vector that points, a unit vector that points directly to the target, walk down that line, and end up out there in 3D space. What is that? It's nothing more than this and this and this. If you look back at the previous relationships, if you multiply this times that, you get AX. And you multiply this times that, you get AY. And you multiply this times that, you get AZ. We'll do a lot of problems with this so that it'll make sense. Okay, so we're at 1149 up here, and this deserves a little bit of time that we need to spend and think about it. So what I'm going to do on Monday, I'm going to pick it up right here. I will try my best to bring the tablet that I've got right here and try to figure out how to manage the classroom the same way I'm managing here. I think it's a much better experience to do something like this, but we'll see what I can do. But we'll go from here, and I'll see you either online or in the classroom. You do not have to come to class. You can pick up the live stream anyway and fill out the word of the day. So it's kind of up to you. So I guess I'm going to drop the stream, and we're going to go on. See you Monday.